Let's review the change of base formula. So log base b of x is equal to the fraction log base a of x over log base a of b. Now the formula looks a little strange, so let's just look at a couple examples. So first of all, we can write log base 5 of 8 over log base 5 of 2 in the following way. Notice how this certainly looks a lot more like the right side. So the a's need to match here and there, and they are both 5. X would be 8, and b would be 2. And so then we write it to look like log base b of x, then this would be log base 2 of 8. You'll notice that over here log base b of x has no a's in it. Now that's fine, we'll just use the formula exactly as it's written, and log base 2 of 8 simplifies further to being the number 3, because log base 2 of 8 is the answer to the question 2 to the what power is equal to 8. Now let's use a change of base formula on log base 3 of 4. So we can rewrite that. It looks certainly much more like the left side now. 3 is b and 4 is x. But then if we're going to turn it into this fraction here, there's no a on the left side, so we actually have to pick. So you could pick a to be 9. So you can have log base 9 of 4 over log base 9 of 3. Or you can pick a to be 7 and have log base 7 of 4 or over log base 7 of 3. It seems a little strange, but when turning an expression of the form log base b of x from the left side into what you have on the right side, you need to choose your own value of a. And so we could also have rewritten log base 3 of 4 as log base e of 4 over log base e of 3. And just another way to write this, because of the log base e just as a shortcut being written ln, we could write ln of 4 over ln of 3. As another example, log base 5 of 13 could be rewritten ln of 13 over ln of 5 due to the change of base formula. Now let's recall the definition of radical. So way back when we looked at the nth root of a equals y, where y to the nth is equal to a. This definition of radical is important. Sometimes people try to ignore this completely, and people tend to do fine with square roots, but then when it comes to cube roots or fourth roots, people struggle. So there's a definition. This definition of radical is helpful to consistently think about what's actually happening. And just as a review, to simplify the third root of 8, well, the third root of 8 is equal to 2 because 2 to the third power is equal to 8. All the color coding up there is meant to help. In the same way, the definition of logarithm is meant to help. So log base y of a equals n if and only if y to the nth is equal to a. So to simplify log base 2 of 16, log base 2 of 16 is equal to 4 because 2 to the fourth power is equal to 16. Make sure all of the colors that are being used here make sense with the definition of logarithm. Take a look at what we have. The y was the 2, the a is 16, and we didn't know maybe yet when the question was just here, log base 2 of 16. We didn't know what n was, so that's why we set up a thing that looks like this. 2 to the something is equal to 16. And we got 2 to the fourth is equal to 16. So compare, okay? Use the definition of radical and use the definition of logarithm when you need these. So when you see third root of 8, we're really just trying to find the missing base. We had to answer something to the third is equal to 8. What about logs? So like in our example, log base 2 of 16, now we're trying to fill in the missing exponent. 2 to the something is equal to 16. In both cases, a definition was necessary, right? So apply the definition of radical or apply the definition of logarithm. Use definitions, whichever one's appropriate. If you don't want to call this a definition, well, this is what I'm calling it, but you got to use this. You got to reference what's in the box when dealing with a radical. You got to reference this when dealing with a logarithm. So here's the definition of logarithm again, just stated using different variables. So log base a of 1 equals 0 because a to the 0th power equals 1. Log base a of a is equal to 1 because a to the 1 is equal to a. Keep track of this a here is that a, and then the a in the parentheses here is this a out there. Log base a of 0, well, that's undefined because a to the what equals 0? There's no answer to that question. There's nothing you could put where the exponent is. A to the, fill in the exponent with what would you fill in so that the result will be 0? It just wouldn't happen, right? Another way to say this is that we can say that log base a of 0 here doesn't exist because the domain of logarithm is 0 to infinity. Remember that we've already discussed that the input to logarithm has to be bigger than 0. Yeah, said differently, the input to logarithm must be greater than 0. So we can't feed in as the input to the logarithm, the number 0. This is why, this language sounds funny, input to logarithm. This is, if so, you need to make sure to use the language. Don't say log a 0. Don't just write log a 0 without thinking about how to say this. Say this in your head. Say log base a of 0. Be sure to say that word of. That word of is now going to indicate that the next thing you say right after the word of is the input to your function. Okay, let's also practice and review what happens because the input to every logarithm must be greater than 0. So to find the domain of f of x equals root 14 minus x plus log base 2 of x plus 10, we want the thing we're square rooting to be greater than or equal to 0. So that is, we want 14 minus x to be greater than or equal to 0. And we also want the input to the logarithm, in this case x plus 10, to be greater than 0. So in the end, we want x to be less than or equal to 14, and we also want, or we need, x to be greater than negative 10. And so the domain here is parenthesis negative 10 comma 14 bracket. That really is the domain. Just to follow up, negative 2 is in the domain. Yeah, negative 2 is a number between negative 10 and positive 14. So that means f of negative 2 makes sense. F of negative 2 should be defined, or f of negative 2 will be a number. And let's just compute what number we get. So we'll have root 14 minus negative 2 plus log base 2 of negative 2 plus 10. So neither of these, neither the root nor the log will distribute. Just simplify what you have inside. So you have root 16 plus log base 2 of 8. So the root 16 simplifies to a 4. Log base 2 of 8 simplifies to 3. So we end up with the number 7. There, we got a number. F of negative 2 should be defined. We should get a number. And we did. That number we got was 7. So don't be bothered that negative 2 is a negative number. We worked it out to ensure that as long as we plug in for x a number between negative 10 and 14, excluding negative 10, including 14, we will not end up square rooting a negative number, and we will not taking the log of 0 or a negative. We will ensure to be taking a log of a positive number, and we will not square root a negative number. Okay, just as a recap, review that to find domain of a function, it was just the principle we were applying, but there just wasn't much room for it on the last slide. We want, or we need, the contents inside our square root to be greater than or equal to 0. We've got to avoid the denominator equaling 0, and we need, or we want, the input to a logarithm to be greater than 0. So let's find the domain of f of x equals 2 to the x plus root 2x plus 20 all over x squared minus 51x plus 50, then minus log base 5 of 90 minus 3x. So, well, we need to avoid the denominator being 0, so I've got to avoid x squared minus 51x plus 50 equals 0. If we factor x minus 1 times x minus 50 equals 0, we need to avoid x equals 1, we need to avoid x equals 50. We also want the contents inside the radical, inside the square root, the contents inside the square root, to be greater than or equal to 0. So we want 2x plus 20 to be greater than or equal to 0. If we solve that inequality, we're going to get x greater than or equal to negative 10. We also want the input to the logarithm, so that's 90 minus 3x. We want that to be greater than 0. So if you work that out, add 3x to both sides, divide by 3 on both sides, you get 30 is greater than x, or if you want to write this just differently, we want x to be less than 30. So piecing this all together, the domain should be bracket negative 10 comma 1 parenthesis union parenthesis 1 comma 30 parenthesis. So this might look a little funky, so let's just kind of go through real quick here that x should be greater than or equal to negative 10. So at the minimum possible number for x would be negative 10. So we start with that, and we keep going until, okay, 1 has to be avoided, so the 1 parenthesis union parenthesis 1. And then we keep going until we get to 30, and then we can't include 30, so parenthesis, and then x at the largest should be a number just slightly under 30, like 29.99, right? So 30 parenthesis. And then you might say, well, what about that x equals 50? Well, the number 50 is already avoided as an input because we needed x to be less than 30. We required x to be less than 30, so we stopped. We already stopped with x has to be less than 30, done. So there's no additional interval to include here. What about 2 to the x? People tend to ask about this thingy in the numerator. 2 to the x, you don't need to do anything about it. What about it, right? So 2 to the x is not the same as log base 2 of x. Don't just accidentally swap 2 to the x to mean log base 2 of x. These are not the same. If you graph these two things, they're not the same. They are related in that the graphs of these two things are diagonal flips of each other. But beyond that, 2 to the x is just some other piece here, and it doesn't this exponential function 2 to the x doesn't cause any issues with, the square root or the denominator equaling 0 or input to logarithm. It's not one of the three issues. So it's just hanging out here, and it does not affect the domain. So it does not affect the set of valid inputs. Of course, having the 2 to the x here would change what number you get for output as opposed to if this weren't here, but it doesn't affect the domain being the set of valid inputs.